So again, in this video, there's not really anything new, but sort of maybe slightly new applications, but the physics that you already know and love is the same. So applications of resistors. So there are a number of applications that we're going to go through. So first of all, the obvious one is producing heat. So the energy change in a resistor is electrical to heat. So resistors can produce heat. And the power dissipated in a resistor is given by current times voltage, um, current squared times resistance, or voltage squared over resistance. And energy used is given by power times time. So all those equations you have come across in National 5. So power equals IV, power equals I squared R, power equals V squared over R, and energy equals power times time. So you may need to use any of these equations again in higher, so just be aware of them. They are on your equation list. So for example, the dryer has a push button operation. It has an automatic shut off which can be adjusted to between 20 and 50 seconds. It has a heating filament which develops 2.2 kilowatts when connected to a 230 volt supply. A, calculate the resistance of the heater element. So what have we been given? So we've got the voltage, it's 230 volts. Sometimes it might just say main supply, by the way. It won't actually tell you the voltage, but if it says main supply, you know that the voltage is 230. Power is 2.2 kilowatts, so 2.2 times 10 to the 3 watts. And we want to know the resistance. Okay, so we haven't been given anything else, so we're going to have to use an equation which has got V, P, and R in it. So P equals V squared over R. So 2.2 times 10 to the 3 equals 230 squared divided by R. And R will be 230 squared divided by 2.2 times 10 to the 3, which is 24 ohms. And part B. Calculate the minimum amount of energy that could be used in one operation of the dryer. So we're told that the time can be between 20 and 50 seconds. So the minimum would be 20 seconds. So energy is what we want to know. Power we've been given, we know again is 2.2 times 10 to the 3. And the minimum amount of time that it would be on for is 20 seconds. So energy is power times time. So 2.2 times 10 to the 3 times by 20, which comes to 44 kilowatts or 44,000 joules. Okay, so nothing new there. Everything's relatively straightforward. A second use for resistors could be current control. So we know that the higher the resistance, the smaller the current. So resistors can be maybe used to adjust or limit the current in a circuit. So for example, volume control. So you can use a variable resistor to change the current that's in the circuit. So for example, this question number 2. Calculate the maximum and minimum currents through the load resistor. So the load resistor is permanent, it's just 3 kilo ohms, but we've got this variable resistor that goes from 0 to 2 kilo ohms. So obviously the maximum current will be when this resistance is smallest, and the minimum current will be when the resistance is biggest. So max current when R is the smallest. So when R is smallest, R will be 0. The variable resistor will be 0. So I should probably say actually R of the variable resistor is 0 because we've still got the resistance of the 3 kilo ohm load. So the current will be voltage divided by resistance. So 12 divided by just that 3000 on its own, which comes to 4 times 10 to the minus 3 amps. And the current would be minimum when the resistance of the variable resistor is at its maximum, so 2000. So voltage divided by resistance again, so 12 divided by 3000 plus 2000 in this case. So 12 divided by 5000, which is 2.4 times 10 to the minus 3 amps. Another use could be in current and voltage conversions. So if you have a variable resistor in a circuit and a fixed resistor there, you can connect it to an oscilloscope, and the oscilloscope will indicate the potential difference across the resistor by, you can count up how many volts per division it is. So in this case, we've got 5 volts per division given to us there. 5 volts per division there. So each how many divisions we've got? 1, 2, 3 divisions up. So the voltage reading from that oscilloscope would be 3 times 5, which is 15 volts. If the current in the circuit is increased, the potential difference across the resistor will also increase because V equals IR. So if I increases, R will also increase. It follows that the trace on the oscilloscope will correspond to the current in the circuit. So calculate the current in the circuit shown above. So we've got the voltage of that resistor is 15 volts. We just worked it out by looking at the oscilloscope. So the current is the voltage of that resistor divided by the resistance of that resistor. So voltage is 15 volts across it, and the resistor is 10 kilo ohms, so 10,000 ohms. So that comes to 1.5 times 10 to the minus 3 amps. So we can use it to help us find the current. Another use that you have seen before as well is potential dividers. So potential dividers, and if you're a bit rusty on this, you can go back and watch the videos that I've made for my S4s. Potential dividers are two resistors in a series with each other. And we know that the voltage is shared between resistors. So the bigger the resistor, the more of the share of the voltage it will get. So resistors may be used to obtain different voltages from one supply. The arrangement of resistors is called a potential divider. So we'd use this voltage here, if we put a voltmeter across here, we could use that voltage to then go on and provide voltage to something else, like a transistor or something like that. So we can change the resistance of the resistors to change the voltage out. So the values of the resistors may be chosen to give any value of output potential, V out, between 0 volts and the supply voltage. So the voltage of the supply splits between the two resistors in proportion to the values of the resistors. Therefore, the output potential is the same fraction of the total voltage, Vs, as the resistor R2 is of the total resistors. So in other words, V out divided by the supply voltage, the total voltage, is equal to the resistor that you're measuring the voltage out across divided by the total resistance. So, but in a more familiar way, we have been writing the potential divider equation like this. That's where you're more used to looking at like, but that's just a rearrangement of what I wrote earlier. So more complex potential dividers can also be made by connecting more than two resistors together. So first of all, part A, calculate the output voltages for the following potential dividers. Answers may be checked experimentally. Well, we can't do that at the moment. So for this one, V out equals R2, so 2.2 kilo ohms. If they're both in kilo ohms, you don't need to change it to ohms because it's just a ratio. So you'll be dividing the 1,000 anyway. Divided by 1 plus 2.2 times by the supply voltage. And that comes to 4.1 volts. I'm sure you're all very familiar with how to do these. And for the second one, R2 is now in the opposite place. So we've got 1 divided by 1 plus 2.2 times by 6, which comes to 1.9 volts. So you're just using the potential divider equation to work those out. And couple more examples. I'm sure you can do these. You can whiz through them yourselves. So for this one, we've got V out equals 10 divided by 10 plus 1 times by 6, which comes to 5.5 volts. And for this one, we've got 10 divided by 10 plus 1 times by 4.5, which comes to 4.1 volts. And for B, there are some design challenges. Now, you don't really need to do this, but what I'll do is I'll supply you with some answers, a screenshot of the answers for these, and then you can have a go at them if you want to, but if you want to skip part B, you can do. But it's just a bit of a challenge if you fancy having a go at it. And the effect of a load resistance on an output voltage. So we're still looking at our potential dividers, but suppose that the output from a voltage divider is used as a voltage supply for a particular device, so a lamp or a motor. The resistance of that device is called the load resistance. This load resistance may affect the output voltage from the potential divider. So it's basically like putting another resistor in series with R2. Okay, so an example here. A potential divider consists of a 9-volt battery connected to a 20 ohm resistor and a 10 ohm resistor as shown. So a normal potential divider. Calculate the output voltage. So that's your normal potential divider equation. So V out equals R2 over R1 plus R2 times by the supply voltage. So it's going to be 20 divided by 20 plus 10, which is 30, times by 9, which comes to 6 volts. Then, the output from the above potential divider is connected to an electric motor of resistance 30 ohms. Calculate the voltage across the motor. So we've still got the same resistors. So we've got a 9-volt supply here. We've got 10 ohm there and a 20 ohm there. But now we've got a motor with a resistance of 30 ohms connected in parallel. So that's 30. Okay, so now we want to know what the voltage out across the motor would be. So we want to know the voltage out here. So what we need to do is we need to find the resistance of those two because they're in parallel. So if we call that Rp, 1 over Rp equals 1 over 20 plus 1 over 30. So Rp would come to, remember you have to flip it over at the end, 12 ohms. So realistically what we actually have is we've got a potential divider with 10 ohms and 12 ohms. And we want to find the voltage out there. So potential divider equation again. So V out equals, in this case, R2 is 12, divided by 12 plus 10, so divided by 22, times by 9, which comes to 4.9 volts.